I'm an open source maintainer. Yeah, I used to work on like plasma physics stuff and then oceanography. I'm a maintainer of xarray and active within the Pangeo project and also like Zarr related things, which is this talk is mostly about. I now work at this startup called Earthmover, which is one of the sponsors of the conference. It's a public benefit corporation. So I'm going to tell you a little story. So at the last job that I had at this climate science nonprofit, I was asked to cloud optimize some data to make a bunch of netCDF files ready for consumption on the cloud. And I thought this was going to be really easy. And I sort of promised it would be easy. And I never really did it. And I think now I've finally done it, even though I no longer work there anymore. But it was such a pain to do this that I ended up writing a new package. And what was previously like practically impossible for me to do now is like roughly 3 lines of Python-ish. And the package is called VirtualiZarr because it virtualizes Zarr, other formats to look like Zarr. But then in combination with this other package that was released since the conception of the VirtualiZarr called Icechunk, you can use this for a wide category of array-like datasets. What's really nice about this is that it avoids copying the data. So you're able to basically access pre-cloud archival file formats in the cloud efficiently without copying the actual data. So if you have like a petabyte of data, you don't need to copy another petabyte. I'll talk about that in more detail. It also plays nicely with Icechunks. One of the features of Icechunk I'm going to talk about, multiplayer mode, which means that you can add more of this data, cloud optimize more of your data, and users can still read it whilst it's being updated. A lot of people were involved in stuff in this presentation at various points in time. Particular shout outs to the names here, and a lot of different organizations, including my previous employer. So the actual data set was this thing called the Seaworthy Ocean Alkalinity Enhancement Efficiency Atlas. The science of it is interesting, but for the purposes of this presentation, it's essentially an ensemble of simulations arranged in a grid. It's like a big parameter scan. The data was like sat in raw form on S3 thanks to this other nonprofit called Source Cooperative that provided the bucket through the AWS Open Data Program. And you can think of it as just like this enormous grid of netCDF files. But the problem is like netCDF is not a cloud-optimized format. And the data was fairly large, but there was a lot of individual files. And the grid was actually like multi-dimensional, and the data itself was multi-dimensional. So if really the whole thing was logically this like 6-dimensional entity. Because you have the original files are 3D, time, and then there was 2 ensemble dimensions in the grid. But now we can just about get this processing this data into a cloud-optimized form down into a few lines of code, 3-ish. The important lines are this call that's deliberately supposed to look like xarray syntax, which I'll talk about later, which scans over all of the files in the bucket and assembles them automatically based on their coordinates, creating references to the data inside them. Then you write those references out into Icechunk, and because Icechunk is basically a database, the third line is when you commit that transaction to the database. The actual data, when you know what's in there, as a whole collection can be visualized in these like beautiful ways. This web visualization thing was built by some collaborators at Carbon Plan, and basically if you click on this, then it shows this like plume of evolving. It's as if the data set is about as if you dropped some chemicals in the ocean basically and watched them like move across. And so if you actually already know what's in this data set, then it's very cool. But the problem is the way it's actually distributed, like the way it was given to me, is not with this nice like overall structure. It's just this like complete pile of like of files where I have very little idea of what's in them, and a user that is pointed to the S3 bucket has like no idea what's in them, and there's 500,000 of them, and they're organized in a pretty complicated way. But really, we as the data distributors, so this is a problem because this is often what people passes as a cloud data archive. Like it's in the cloud, but like that's it. And this is often the result of people naively lifting and shifting their data to the cloud, which some large organizations are sometimes guilty of. But the thing is, we know as data providers that the data does actually have structure. In geospatial jargon, we might say that this is level 3 data, which basically just means it's part of like a larger homogeneous grid. But the real problem is that the data is not cloud optimized, as I mentioned. What that means in practice is that a client code of a user that's trying to access this data set has to look at metadata. It has to look at not just metadata in each file, but metadata that's spread throughout the file, which on a local file system is not a big problem, but in object storage is very slow. You have to do this check for every single file, iterating over all of them, just to know that they even form a logical grid in the first place. And if you naively called xarray open multi-file dataset, then that is effectively what it would do. It would glob over all the files and look through all of them. It would take a long time to process each one, and it would iterate over all of them. If you want to know like why it's so slow to do it on a single file, I have a blog post about this that I wrote a couple of months ago, which basically explains why in the worst case it could take like a minute per file just to get the metadata from object storage because of S3 GET request latency round trips, basically. But if we do this like worst case minute per file multiplied by 500,000 files, that's an entire year just to find out what is even in the data set, just to open it. And this is what we mean by not cloud optimized. It's in the cloud, but it's not cloud optimized. So the conventional solution to this is to rewrite the data in a cloud optimized format. And it's an array data set. The whole thing is logically a datacube, so we could rewrite it as a massive Zarr store, right? But the problem with doing that, well, the good thing is that now opening it is enormously faster. And the basic reason is because when you write it in the Zarr format, all the metadata about what the grid structure is all in just like one place in a little JSON. So all you have to do is get that one JSON, and you've reduced like thousands of sequential GET requests to just like basically a couple of GET requests, and that's why it's so much faster. The downside is that in order to do that, conventionally, you have rewritten the data in a different format and therefore used more space. And so if our original data set was 50 terabytes compressed, we've now used double that. For some large data sets, like big NASA data sets, that like they have petabyte archives, that's like an enormous cost just to basically reorganize metadata. But what if we could just make the netCDF files look like they were a Zarr store and get that nice like fast reading property without actually copying the data? So we want to somehow make the netCDF look like Zarr. We want to disguise it as Zarr. And we need some kind of layer that looks like Zarr but points to the original files. And that layer, we can use Icechunk for that. Because Icechunk has this feature of storing virtual chunks or virtual chunk references. For context, Icechunk is this open source project, a transactional cloud-native storage engine for Zarr. It works together with zarr-python 3 and xarray, so you can basically read from it using the zarr-python API, just like a normal Zarr store. It supports virtual chunks, crucially, for this. It's implemented in Rust, so the I/O is super efficient with a thin Python wrapper, which is how you can read from it with Python as well. And it's an open source project. I'll talk more about it in a bit. But this is an Earthmover open source project. But to get the virtual chunks into Icechunk, we first have to create these references, these virtual references, and that's what VirtualiZarr does. So we import the VirtualiZarr library, we call open virtual dataset on our netCDF file, and what we get back is this like special xarray dataset which contains a bunch of information about like where to find every chunk, basically. So for Zarr chunk key 000, it's in this path, and you have to, the HTTP range request has to start here and end here. And that's what we mean by a virtual reference, and a bunch of them together is a chunk manifest. And it's VirtualiZarr's job to inspect the netCDF file and extract this kind of information, which will depend on the specific file. It also extracts all the other metadata as well. I just haven't written this out here. And then the problem is like, we've got to do this not just for one file, but for all 500,000 files. And then we need to combine them all together into a logical data cube. But combining chunk references from different files is effectively an array concatenation problem in chunk space. And so we can use that. This is why we do it with this weird Xarray dataset, is because Xarray already has a really nice API for doing multidimensional concatenation problems. So by making these weird like chunk manifest classes, putting them inside an Xarray dataset, we can end up just reusing the Xarray API for free to do this like a potentially like three-dimensional concatenation problem. And then once we're done with that, we get like one coherent representation of all of the chunks in the dataset, and we can write that back out to the Icechunk as the database that stores our virtual chunk references. You can also write it out to the Icechunk format, which predates Icechunk. So that's what we need to do. We need to call these functions on all of these files and then combine them. But how are we actually going to scale it? So this is really a map reduce problem. One way to think of it would be like when you do Xarray open multiple file data set, we're kind of doing basically the same thing, but we're doing, instead of like opening the data set the normal way Xarray does, we're opening it virtually to extract these references. The M means multiple files. We've got to do it across all our file paths. That step of running that function across all the files is a map step. And then after that, well, the way we're going to do that bit is we can do this serverlessly because it's fully embarrassingly parallel. So one way to do it would be just to have like one Lambda function per function call that we need to do on each file. So one Lambda function per file. And this is nice because we can spin up a bunch of Lambda functions extremely quickly. Each one of them calls open virtual dataset once on one netCDF file. That's the map step. Then we need to, and then if you've got more than 1,000 files, typically your AWS account only lets you do 1,000 Lambdas at once unless you ask AWS nicely. But then you need to combine them all together. So you've got to take these little virtual references and concatenate them back together, your little data sets that are returned by the functions, and concatenate them all together. And that's the reduce step. But the thing is that what we're reducing here is not the actual data. It's just the names of the locations of the data. So it's millions of times smaller than the real data, which means that we can actually just send this information back over the network and do it on your laptop. And it works fine, even though we're doing it for like 500,000 files. And then the final step is to dump those references into Icechunk. And so when you actually run this, then it looks, this is like a little bit janky with some unreleased code, but what I want you to see here is that like we've got 700 Lambda functions that have run in about 20 seconds, and then we're doing another batch and we're going to run like another 700 Lambda functions in another like 20 or so seconds, and rapidly like using this like serverless scaling approach to just like quickly chug through all of this data. And then we get a throughput of something, we're like passing these non-cloud optimized files at something like 10 gigabytes a second, which isn't super fast, but that's because they're not cloud optimized yet. We're running this from the laptop, and then the scaling is happening in the cloud, but the reduce step is happening in the laptop. It's batched, which I'll come back to in a minute, like each loop. It's also resumable because we commit each batch to Icechunk. So and that's transactional. So if it fails afterwards, we can pick up from the last successful transaction. And this is like pretty general. Like this is just, I've just done this for like arbitrary netCDF files. And it roughly 3 lines of code-ish, 3 important lines. So some of the stuff I use to make that is coming out in upcoming VirtualiZarr 2.0 release, especially for some of the open virtual MF dataset bit. But VirtualiZarr and Icechunk work together today, so you can try it out. Also, Icechunk 1.0 was released today. So Icechunk is now officially production ready. And importantly, this means that the Icechunk format that sits underneath the Zarr API is stable and backwards compatible with an open specification. So one thing you might be wondering is, whilst I'm adding more data, what happens if someone reads? Because each loop iteration is adding more data to the Icechunk store. And real-world data often needs to do this. So for example, if you have a NASA satellite that takes like images, maybe as it goes around the Earth, it takes more images every hour or something, and you have like a regularly updated data set. And you can't wait until it's like fully done, because it will never be fully done. Users need to be able to read from it whilst it's being updated. And you want to see a full history of changes. And this is what Icechunk gives you. You have these like individual commits and a history of snapshots, a history of state of the store. You also want users to be able to read the data, like not just at each snapshot, but literally while new data is being ingested, which with normal Zarr is not possible, because if a user starts writing an update and they start writing more chunks or start messing with the metadata, whilst they're messing with the metadata, if somebody else reads it, they will see some inconsistent state. And that's a danger all up until the first user has finished writing the update. This is just like a fundamental limitation of Zarr, which stems from the fact that Zarr isn't a single monolithic file format with like locks. It's spread over many files, which has scaling advantages, but this is one of the disadvantages of it. But with Icechunk allows you instead to do what you could call multiplayer mode, where you have database-like transactions that enable safe collaboration. So instead, all updates, unlike normal Zarr, all updates occur with a transaction and create a new snapshot, which the technical term would be serializable isolation between these transactions. And the readers only ever see what's been officially committed. And this is done without locks on the reading of the data. And then it basically has a way to resolve merge conflicts as well. And this is all done like in S3, in object storage, without running a continuous database process over the top, which is pretty cool. And so this really makes, Icechunk really promotes Zarr into being more like a database, because this is like a key feature of what is normally considered a database. And so overall, this, you can think of it as like Git for Zarr, Git-like version control for the array data. You have like, it has branches, you have a main branch, it has tags like Git does. You can create new branches and then you can merge them back in or rebase or whatever. So that's like a very powerful feature of Icechunk that's super useful for this kind of ongoing ingestion problem. The example I gave was netCDF, but what other file formats could we do this with? So currently VirtualiZarr understands a few different file formats and some other important ones coming soon. But actually in VirtualiZarr 2.0, we have this like very general framework for writing your own custom parser for a more niche format if you want to support it. So for example, there's someone's got an open PR for a parser for Hugging Face's safe tensors format for storing ML model weights. It's just an example of a like custom binary format that ultimately is just an array thing. The parser definition is really just a callable that just takes like the URL and returns this like VirtualiZarr manifest store class. And the reason this works is because ultimately everything is just, all these file formats are just arrays. The parser also enables something quite neat that wasn't possible in earlier versions of VirtualiZarr. Because the parser returns this funny manifest store class, and this manifest store is a valid zarr-python store class, like it follows these zarr-python store ABC, then zarr-python or xarray can read this store directly. It uses the obstore Rust crate, object store Rust crate, to actually read the data under the hood. And so this means you can do code like this. You can import, like, if there's a parser for a TIFF file, you just call the parser on the TIFF file, you get this manifest store back, and then you can call xarray open zarr directly on that manifest store. Like, nothing's been saved to memory here, but now this xarray dataset is reading data directly from the TIFF file. Which means that you don't need to, in order to read the data from the TIFF file, you don't actually need to serialize to Icechunk or Icechunk. Which means, in other words, you're able to use VirtualiZarr as a runtime translation layer to read any parsable file format as Zarr. So it's kind of like an adapter layer, a little bit like the Oxbow presentation from yesterday, which was doing something similar for tabular data formats in genetics. This is a little bit like an array equivalent of that project. Doing this only really makes sense in certain scenarios. For example, if you're doing an object storage, it would only really make sense to do this for an already cloud-optimized data. Or if you're running it on a local file system, then it's quite useful. The reason is that running the parser itself takes a while if you're running it on non-cloud optimized data. If it was quick to run the parser, there would be no need to cloud optimize it. So in summary, slightly ahead of time, level 3 or 4 datasets, by which I mean just like things on big grids, doesn't have to be geospatial, are often in archival formats, but those archival formats often have zarr-like array structure to them. Creating a virtual Icechunk store allows you to point at the files without copying and duplicating the data. So you could like refer to many, many terabytes of data without copying and duplicating them. You can assemble these like large virtual data cubes using familiar xarray syntax via the VirtualiZarr library, which means you don't have to learn like a new API that you didn't already know. And Icechunk's transactions allow you to do incremental updates to the data as new data arrives while still retaining the safety for users who are reading it. So overall, if we compare like having a non-cloud optimized format versus Zarr versus Icechunk, you can see that because we are able to get all the advantages of Zarr whilst also avoiding increasing our storage requirements. That's my talk. Take questions. Thank you.
All right, we're going to open it up for questions here. And I already see a couple that came through. So from Ken, Ken asked, when model output can vary greatly in its arrival times, for example, weather models, is there a good way to notify users when new data has been received, integrated, and is ready for consumption?
That's a good question. I think it's fairly orthogonal to what we're doing here, because it's the same thing as saying like, how do I alert users when like something specific in my S3 bucket has changed? I think that there's like Amazon services that will do this kind of thing for you, but it's not something I'm super familiar with. But yeah, if you wanted like a notification system, that would be on top of the actual storage. Yeah.
We have another question from Max that says, do you think this workflow is in a stable enough state for data archive centers to put into production?
Icechunk, certainly. VirtualiZarr, be nice to release 2.0, but generally, yes.
Cool. Jared asked, how is VirtualiZarr different from xarray-like?
Yeah, good question. What about xarray-like? So xarray-like was kind of an inspiration for VirtualiZarr, but one way to think of VirtualiZarr is a rewrite of a xarray-like project. But first we have to disambiguate. xarray-like is really two things. It's a Python package, and the VirtualiZarr Python package directly is an alternative to this, and the advantage being that it has an easier API to use. The second thing that xarray-like is a format for storing the virtual references. So xarray-like can store them as JSON or Parquet. And the Icechunk format is an alternative to that part of xarray-like. VirtualiZarr can actually write to both of these. Like VirtualiZarr has a toIcechunk method. It also has a toxarray-like method, which predates the toIcechunk method. And so we can actually add xarray-like into our table, and the xarray-like, the disadvantage of xarray-like's Python package is that you can't do your concatenation using xarray, which means that like one of the reasons that I even got into this in the first place was that trying to express my three-dimensional datacube concatenation was basically not possible with the xarray API. It was just extremely tricky, but it's very easy to express that with xarray's API. The other thing is that the xarray JSON format, the xarray Parquet format, they don't have database-like transactions like Icechunk does, which is why these are no's here. Yeah.
Nice. Sarah asked, does this work with netCDF files that are compressed in an S3 bucket as well?
Yes. So the chunks are referring to compressed. Oh, if the netCDF file contains compressed chunks, then yes, because each chunk reference is pointing to an individual compressed chunk inside the netCDF file. If you took the whole netCDF file and compressed the entire thing, which I don't think you should ever do, but I'm sure somebody has done it, then I don't think that would work, because you can't do, the problem with most compressors is you can't do like a partial read from something that's compressed, and you still need to be able to like do a partial read. Yeah.
And then Nick asked, does VirtualiZarr also parse information regarding the chunks inside of the netCDF or H5 files?
Yes. Yeah, so you can, if you parse a netCDF file that contains multiple chunks, you'll get back a manifest with multiple entries. Yeah. You can even like parse an existing Zarr store, which has many chunks, and then you'll have like an Icechunk store that virtually references all the chunks in a Zarr store, and it's kind of conceptually very similar.
And then from Beth, how does the concatenation work in practice in something like TIFFs, which may not already have good header hints as to how they go together?
So you're not using the header hints of the TIFF to tell you how to concatenate between TIFFs. The header hints in the TIFF tell you like what is in that specific TIFF, but only the like data provider actually knows like how TIFF 1 is related to TIFF 2. And so in my case with the 500,000 netCDF files, like by examining one of those netCDF files, there is no way to determine like how it's related to all of the other ones. So like that's why the data provider has to come along and run the code to do all the concatenation of them all together. And yeah.
And then from Jared, what is rough estimate for 2.0 with TIFF and COG availability?
I was hoping to get 2.0 done by today, but I overcommitted to SciPy with 2 talks and a tutorial. So there's no blockers to that now, so we could do that like within a week or something, I'm hoping. COG and TIFF support, I've kind of like farmed out to my friends at Development Seed. They're actively working on it, but I don't want to like force them into a timeline. Yeah.
And then from Eberto, it's besides the conversion effort itself, what are some heuristics to decide between creating a virtual Zarr dataset or converting to Zarr directly?
Yeah, very good question. So the main downside of this whole approach is that you cannot change the chunks. Like you are creating references to the existing chunks, but you cannot change the chunks as they were chosen. And so if the chunks are just completely unsuitable for the query that you know you want to do, like if the chunks are spatial but you know you want to do like time series queries, then you can virtualize them and save your storage, but it won't be super performant afterwards. And so in that case, you might want to pay the extra storage cost to create a new copy that has chunks that are better suited for your queries. There's ultimately just like a trade-off between using more storage to make something that's like better optimized to save on querying and vice versa. And so that's the primary scenario in which you might not want to do this, is if your chunks are unsuitable for the queries you know you're going to do. But Icechunk allows you to write both types of chunks, like virtual chunks and non-virtual chunks. So you could even like ingest it virtually with the bad chunks initially, and then like later on, we're like, oh, this isn't great, I'll rewrite the chunks and write them in there.
And then we just have another minute or so maybe 1 or 2 more questions. First, I'll go with Max. What if your netCDF data was chunked poorly in the first place?
Yeah, I mean, same thing basically, yeah.
Nice. And then Nick has a question. How large was the metadata for the example data set? Where does this typically get stored? In another bucket?
I can't remember the exact size, but it ends up being like, I worked out the fractional increase. Oh, I've gone way too far back here. And like the fractional increase is like absolutely minuscule. And sorry, what was the second part of the question? Where does it get stored typically? Yeah, so the virtual references can point anywhere. So they could point to like files in the same bucket, but they could point to files in a different bucket, or they can even be like HTTP URLs. So you can make an Icechunk store that points to like many different buckets if you want to. Yeah.
Okay, we're at time. There's one more question maybe you can answer on the Slack, but thank you so much, Tom.
Thank you.